Now it's my pleasure to introduce the second duo, the second joint lecture by Tomasz Kolencik. Perhaps need no introduction in the MS field, but nevertheless he is professor and head of the Clinical Outcome Research Unit at the University of Melbourne in the MS Centre at the Royal Melbourne Hospital, and he is well known for all the use of the real-world data. We've seen a lot of him, thank you. And Ashkan Pirmani from Belgium. He is a double degree PhD student in Catholic University of Leuven. And his research focuses on the federated artificial intelligence in big data and health care. So the floor is yours.
Thank you, Professor Witthagen. Thank you everyone for coming to this afternoon session and for having us here today to close the program for the shared lectures segment. If I do sound a little bit incoherent, please bear in mind that I'm lecturing at 4 a.m. Melbourne time, but the copious amount of caffeine that I had after my lunch are still working, so I'll try to make sense. In this segment, we will try to build bridges. We'll try to talk about about language of two tribes, the tribe of statisticians and engineers, actually 3 tribes, sorry, and clinicians, and about some of the expectations and where we see gaps and deficits, and perhaps maybe come to the space where we get to propose some solutions. And I absolutely rely on an engineer counterpart for this conversation. So this is how I perceived how we currently tend to use AI in multiple sclerosis. And the classification and prediction are 2 examples that we have, or 2 areas where we have heard ample examples throughout discussions today. Classifications of lesions, brain segmentation, for example, and prediction of individual patient outcomes, patients' futures. You would not see, obviously, I didn't put a decision assistance tools on this slide, because these 2 are actually outcomes that do feed into decision support, and the decision is still in the hands of the clinicians and their patients who are looking after. Prediction is not anything novel. We use it in science. It's actually the elementary approach in most fundamental of the sciences, and I'm a big fan of physics, even though I don't know much about it. But physics is an art of prediction, or science of prediction. It's we're learning from the past about these rules, which we call the laws of the nature, to predict the future. And our predictive models are imperfect and keep improving. Let's take a simple example, gravity. We started from the Newtonian model of the forces. Then we moved through the relativistic models of time-space continuum, through a recent proof of the gravitational waves, and there is more to follow, because we still need to unify this concept with the concept of quantum mechanics. We are not as advanced in MS, but we do predict a lot, and we do that in clinical practice on a case-by-case basis with N of 1, with our experience in read literature, and we combine intuitively the published evidence, so that is the power of the prior knowledge, with the data that we see about an individual patient. A number of areas in which we use this are highlighted here, and the importance of the prediction. We want to make sure that we want to help patients understand what's in the future and potentially mitigate the outcomes appropriately for their predictive individual trajectories, set expectations appropriately to that, organize care in advance and with a little bit of appropriate notice, and also select treatment strategies. The different types of predictions that lead us to achieve these goals are, on one hand, prognostics, individual prediction of the future, but also prediction of individual treatment response. And interestingly enough, also individual modifiers of treatment response, which we are learning about. Let me now run through a few examples of different predictive models of different variety of complexity and focus that have been published over the years in the literature. And the literature is really rich in examples. And here's a very simple predictive model. All the examples that I will use are related to a progression of the disease in some form, in this case secondary progressive disease. What you see here is an example of a decision tree. This decision tree, developed in the Swedish MS registry, basically work with only two inputs, patient's EDSS and age at the time of prediction. And these types of methods do not require optimization through AI. They mostly work through methods such as CAD or even simpler methods. And using the method, the group arrived at a fairly simple stratification of combination of EDSS scores and ages at the time of assessment in the absence of relapses to predict the probability the patient at the given time is being in the stage of secondary progressive MS. And in an independent validation of this cohort, I think in the Vancouver cohort, the performance of this prediction was fairly impressive. With slightly more complex approach, this group from Italy, looked into use of Bayesian methods, which I am a big fan of, even though I'm not Bayesian by religion. But the reason why I really like Bayesian methods is that they eliminate the confusion of interpretation of the frequentist framework that we often see with the p-values and the publication of evidence in the frequentist concept. The beauty is that Bayesian frameworks allows us to integrate the data with the prior knowledge to generate posterior probability. And this Bayesian approach, again, aiming at predicting the probability or identifying a probability of patient having SPMS, identify the usual risk factors such as sex, age at onset, the functional system scores, and particularly long tracts such as pyramidal and bowel-bladder involvement. Here is a slightly more complex approach that tries to utilize a wealth of data at the same time for 53 variables representing patient trajectories and allowing for data missingness, which is quite important in registry research. How do we deal with that analytically? It's a very complex question to deal with data sets that are inherently limited. And one way of getting around the problem of the multidimensionality is a dimension reduction step, which is exactly what we applied here with principal component analysis, quite luckily identifying 3 orthogonal components that allowed us to define patients in different situations by basically 3 values. And adding 2 additional random effects to the model, we have designed a model that is a fairly standard survival model there down the bottom with the Nelson-Allen estimator of the null hazard function. What this all technical terminology leads to is a model that allows us to conduct a prediction in an individual patient, and you see 2 examples here on the right-hand side of the screen of 2 outcomes, disability progression and probability of relapse that a patient is about to experience or likely to experience over the following 4 years from the prediction time point, with 95% prediction intervals showed by the dashed lines. And excuse me. And you will notice that the cumulative hazards of these events, the hazard curves have a shading that is more apparent on this slide with slightly less represented therapies such as mitoxantrone post 2 years of usage, which is rarely used really after that time frame, to represent the density of the data and therefore credibility of that prediction. And this really speaks to the visualization, making the output of an individual prediction accessible to a practicing clinician. I'd like to now highlight one particular study, which was done by the group in Belgium, by Edouard Brouwer with the team. And it is a really elegant application of an AI model to a question of sporadically recorded disability time points over time from a large international registry. The problem that this study is dealing with is the non-linearity of the outcome, also the irregularity of the follow-up. And in order to define the model, the team has specified a confirmed disability progression from a baseline. The baseline EDSS here in the schematic is outlined in blue, and the red points after the blue, they signify here the change in EDSS, with the orange points meaning a confirmation of that change. Now, this is the cohort that was used to develop these methods. Over 6,000 patients with mild to moderate disability around EDSS 2.5 and with fairly irregular but frequent visit schedule and mean age of 32. The practical approach to the variables, number of variables that can be fed into model, led the investigator to stratify them into three strata: static variables that mostly do not change or should not change, and they are only entered once; dynamic features that represent some part of the history defined within the time frame moving into the past; and the third set of outcomes of variables being longitudinal variables. And these are mostly the variables that we're primarily interested in, such as EDSS trajectories, but also relapses and disease-modifying therapies as the modifiers of the outcome. And these four models were compared, and I find this really interesting. Random forest is something that is a standard methodology that all machine learnists would be familiar with. It's a very well-proven model, but its main limitation is that it doesn't work with time series. So they had to engineer an input, and the input representing a single time point around the time of the baseline. Then the second alternative was the Bayesian tensor factorization, and what it does, it constructs a tensor as a combination of level 1 tensors, and it does squeeze outcomes into these serial bins in order to work with serial data acquisition. It's a little bit messy, but it's one step above the cross-sectional acquisition of data points at around baseline. The time-aware recurrent neural networks use, so to speak, the GRU aspect of the gated recurrent units. And basically what this does is it acknowledges the irregularity of the follow-up without squeezing the follow-up into these bins, by adding a timestamp as an additional variable in the matrix. Again, imperfect solution, but it does serve the purpose. And this completely new method, the GRU order Bayes model, which was invented by Edward, this is a really elegant approach that defines first a latent process that underlines everything. By latent, I mean it's an unmeasured process that sits underneath everything that we can measure. And this latent process gets recalculated, re-estimated with the Bayesian paradigm every time there is a new data entry. So our latent process is not static and defined a priori, but keeps changing over time, very much like the disease course. And comparing these different approaches, I won't bore you with too much details. They have arrived at the outcome that the ROC, the area under curve for the overall performance of the model, was very satisfactory for the most advanced model, the GRU order Bayes model. And also the precision recall balance of the model was very good. So the ROC curve is at the top, and the bottom curve is the precision recall model. And just for interpretation, the recall, it would approximate to something that would represent a sensitivity in our typical study, and precision is similar to a positive predictive value. The fine touch that I really appreciate in this study is the attempt to decipher what goes into the model by estimating the variables that are the most influential ones that have an effect on the model. The method that Edward chose to do this is very elegant. He basically left one variable at a time from the model and looked at the deterioration of the performance of the model. And based on that estimator, he saw the last EDS was most influential of the predictors that feed into the model, which allows us to include a label in what would otherwise would be a fairly black box to a practicing clinician. Of course, there are many efforts that use AI in prediction of disability outcomes and SPMS, and here just a sample of few. And I mentioned pattern identification. I will not discuss this at large, but it has been already discussed, but I find a great user base for AI in the pattern identifications. There were much better founded speakers today who spoke to the details of it. There is a little also review mentioned at the bottom of this slide with the images from Arman Esagi's study published recently that allow us to classify the acquisition of disability into three classes. So I will end this segment with postulating two areas of clinically motivated questions which I view as the main limiting factors for the use of AI in conjunction with clinical practice. And that is the importance of validation. Many results that are being published are published in the absence of validation. I would want to highlight that external validation, multiple external validation for any AI-based model is an absolute must and absolute critical step before we can consider that to be credible. A black box nature of the output is another nature. A neurologist wants to understand what is informing the patient's outcome in a certain way. They don't want a machine to do the work for them. They want to be able to think and make their own mind about why this patient is on the severe trajectory or not. And the clinical accessibility, as I mentioned. This tool needs to be accessible without clinicians having to enter tons and tons of data in an online gadget to spit out the results. For pattern identification, we need to be able to interpret the patterns that the AI returns us, and these need to be clinically valid patterns that are associated directly to the clinical presentation of the patients, as was mentioned in the discussion of one of the previous lectures today. And of course, reliability. We want to be able to give the patients information with good precision and good accuracy. And I'll hand over to Ashkan.
Yep. I will get back to this limitation, but first I would like to appreciate for program coordinator and organizer to giving me this amazing opportunity to be here. Definitely it's an honor for me. Although AI systems have repeatedly been shown to be successful in a wide variety of medical studies, we heard many of them today, but relatively few AI tools have been translated into medical practices. Critics point out that AI systems may in practice be less helpful than retrospective data would suggest. This might be an issue of systems may be too slow, they are complicated to be useful in a real medical setting, or there are unforeseen complications may arise when human and AI want to interact, or there is a miscommunication between the AI and healthcare provider. And we have to consider that usually retrospective data would go under extensive amount of cleaning and filtering, which make it less representative of real-world data. An interesting paper has recently published in Nature, AI in Health and Medicine, which is summarized nicely progress, challenges, and opportunities in health and medicine, which is kind of applicable also in multiple sclerosis, which I'm going to talk about challenges today, especially challenges about implementation. And of course, if we are talking about implementation challenges, we should and have to talk about data and its limitations. One of the most popular data types are images, especially in multiple sclerosis MRIs. MRIs and in general, images are dense and large, which brings some hurdle if you want to just fit them as it is to the AI. So how we can tackle these challenges? Obvious one should be just resize it and split it. But resizing comes with the consequence of quality, which we don't want to get lose it, especially in MRIs. If you are really dealing with the lesion, we want to see with the fine detail there. Or split them, just put them in a slice. But our methodology, our framework, our machine should have this capability to draw a connection among them. Or maybe we can just involve humans in it and ask experts to identify the region of interest. I'm messing with something, okay. Before feeding them to the AI, but it also has its pros and cons because we are just adding manual step to the pipeline. Or we can also ask our friend AI using some custom models to work on whole image and data set. But we need some expensive hardware, and we have to realize we cannot often find this kind of tools or models publicly available. The other challenge of real-world data in a real-world setting is unlabeled data set. Shortage of labels required for the supervised learning, type of learning that needs kind of targets and labels for the prediction. How we can tackle this? To overcome this, you can ask your experts to just label them, but if we consider data set size, ratio to the experts, and time constraint, I don't dare to read the last one, but in some cases, shortage of expertise, it's not easy to just go over through this step. Or maybe we can just go to non-expert through crowdsourcing or outsourcing, but definitely it's going to be less accurate than what experts labeling. And we have to consider that if we are just sharing our data with so many people, even if it is possible, we are in a privacy risk and danger zone. We can also use some less supervised models that need less target, like semi-supervised, unsupervised, few-shot, zero-shot learning type of models. but they are not also risk-free. Beast of challenges, bias. Open and advanced challenge from data point of view. Bias is a phenomenon that occurs when an algorithm produces results that are systematically prejudiced due to erroneous assumption in the machine learning process. But where this bias comes from, different way. These are not the only biases, but just for an example, measurement bias, if you are using some specific medical device that captures data and has some noise or specific protocol or just calibration, all of the data produced by that device is going to have that biases. Or sample bias, when we try to teach our system, but we are not really representing full enough or our data is not enough, we are in a sample bias. Prejudice bias, which is a really challenging about the fairness and equity when we are trying to again teach system, but we are using some, let's say, stereotype or unrealistic thing that unfortunately try to teach system, but it's escalated by the system when we want to implement it, and we have some results like Amazon recruiting system, which is, yeah. Or exclusion bias, when we are thinking, okay, maybe this feature is not really important and we are dropping from our analysis, but then it comes also with other consequences and some other algorithmic biases. But let's see how this bias affects and why it's affect. When we do machine learning, we make implicitly or explicitly this assumption. The reason that I'm kind of showing this horrifying mathematical notation is that I want to show that there is a mathematical background about this assumption that we are doing. In machine learning, we are considering that our training distribution, training data, is drawn from the same distribution as our test data. And our aim is to find this P y given by x using a particular algorithm that we are trying to implement. This is a case which we refer, and this is the assumption that we know as IID, identically and independently distributed. And if for some reason we are violating this assumption, should be just comes from natural changes of data or some of the biases that we introduced, or if we are doing some collaborative learning, federated learning, of course we are in kind of trouble. Generalization error and underperforming. Generalization error, also known as out-of-sample error, is a measure of how accurately an algorithm able to predict outcome values for the unseen data. In this illustration, for example, we had just a bunch of round-shaped trees in our training data, but we trained the model on it. But when we are trying to introduce new kinds of data as a test data on it, our model unfortunately cannot be generalized over a new type of data set, or it's going to be underperform and go over this root curve. No one solution to tackle bias and need deeper investigation for each use case and case study, and we have to go through, but there are some general recommendations like introduce more data to your algorithm, or just try to prune your data set from that feature adds bias to your system, or use some methodologies and framework that they are less sensitive to bias like Bayesian networks, or use some transfer learning using some pre-trained models. The other side of challenge is building model trust. Knowing how AI and human interact and how AI reaches to a conclusion. Explainability. Black box approach is kind of a known terminology in AI. This is a kind of model that they are not welcomed by clinicians most of the times, because we have some input, some data we are throwing to our model and we are just getting some output, might be interesting. But internal behavior of the code and algorithm is unknown, and we don't want this. We want to know what's happening and what's the process over our data. And we want to just make it clear. We want to know how our algorithm is just go through transparency, understanding of AI model, how it's make decision, and knowing reasoning behind each decision that it makes. And to know more or less the mathematical certainty about the decision that made. Great effort recently has been made to bring some light to the spectrum, explainability spectrum. We have some kind of beloved models in clinical domain, like logistic regression as a white box model, because they're kind of easy to understand and interpret and know what's happening about our data, all the way to the black box model like deep neural networks. Of course, there are also some in-between models like gradient boosting models or generalized additive models. Two of the most famous methodologies in XAI or explainable AI is kind of LIME and SHAP, which they have got recently super hyped, especially SHAP, which I'm going to show an example of it. This is a research study that has been published recently. They're trying to predict disease activity in patients with multiple sclerosis, and they're trying to see who will have an onset of a disease in 3 to 6 months. This is the SHAP, one of the SHAP's output, and how can we interpret this is that if we have a deeper look at the figure, we can see treatment weeks and new combined unique active lesion count. They have most contribution to our model's output, and we can understand that it was kind of relevant domain knowledge that we know also from multiple sclerosis, that it's kind of aligned and it was not about some random feature that our model got. The other crucial element of trustworthiness is accuracy and validation. Healthcare providers tend not to trust a model that they are not really performing well, which completely makes sense. 50%, 60%, 70%, even, it's just not a model that they want to trust. It's more or less the same as tossing a coin. I'm not going to argue that figures, but my main point here is that recently there has been an amazing progress during past couple of years, which we can see performance increase over time, and we already saw some leaps over time, and this will continue, and thanks to all the great improvement done by technological and the knowledge point of view. But what makes this trustworthiness is a real hurdle in a real-world setting is validation. AI studies should be reproducible and replicable. What I mean by reproducible, training a model of given data set should produce a consistent result. It shouldn't be just for my luck, I got really good random initialization and I got a good performance. I cannot go and say, okay, I'm going to say a word with just this model. We need a consistent output. And in my mind, it should be also replicable. Models should perform consistently when trained on other data sets. For some reason, if my model works on my data set very well, and if I cannot really leverage that knowledge from that model, it's going to make it less interesting and less helpful, if I wouldn't call it useless. And I think we could blame that data sets, codes, and models are not often published open source, and we cannot really use them as a playground to just build models over that, use that training data to work over it, and we have almost no playground to see how can we go further. Jeffrey M. Drazen, editor-in-chief of the New England Journal of Medicine, kind of most prestigious journal in general medicine, he believed that they should never ever publish a research study unless it has been validated on 2 independent studies, which is a kind of reflects how it's important to just get validated the research that being out, because he was in lots of trouble that he had to take down so many researches because they were not as much as promising when they want to implement it on other population, which is, of course, it's not the case that authors there want to just bluff or show everything is beautiful and nice. That's reason of some challenges and unforeseen things. There is no one prescription and magic solution for all the challenges, and at some point we are kind of in this gray zone. We have to do some trade-off between our desires and what is possible and feasible. To just make the comparison, I've just name dropped some of the challenges. I'm just going to high level compare 2 methodologies as deep neural network one side and regression the other side. We know that deep neural networks, they're kind of hungry for data, and so if we have so much data, that would be a good stop to go there, because we know that regression, they don't need that much data, but deep neural networks have amazing accuracy compared to the regressions. But explainability is not the thing that they are shining there compared to the regressions. And of course, if you are working on some kind of images, they also need kind of computational infrastructure to train them, which is also regression is kind of free from it. Privacy is a kind of cost that if you are working with so much data, we have to pay in deep neural networks. There are some research going about how robust deep neural networks are. There have been some research is going about backdoor attacks. They could extract, reverse engineer some information from the layers. But that's not really the case about the regression compared to the deep neural networks. Validation is the thing that they're kind of both lacking this side. My last point before passing to Thomas, I have name dropped some of the challenges, and I would like to highlight that machine learning community, data science, is aware of them. They have developed and is still working on solutions to address these challenges. And I believe there is a bright future ahead of us. Maybe not for AI versus human, but definitely for AI along human.
Okay, let me, in the last couple of minutes, propose a case. And the case is around progressive MS, as I mentioned several times before. This is a schematic that the MSologists are familiar with. Basically, what we see here is that the rate of progression and neuronal loss increases with time with MS, and the degree of episodic focal inflammation does decrease over time. Now, when can we start identifying the signs of progression? And you have heard about this concept of PIRA that has been really emerging lately and really frequently mentioned in the field. Here is a study utilizing data from randomized controlled trials that looked at the definition of two different types of progression: relapse associated worsening and PIRA, so progression of independent of relapse activity, looking visually on the left-hand side on how they are defined. And interestingly, in this trial, even in these two trials of ocrelizumab versus interferon beta, the association was largely contributed to by the PIRA, the progression independent of relapses, and here we're talking about the OPERA studies into relapse and remitting disease. Does this, however, mean that PIRA is something that we haven't recognized, and it's a progression that starts early in the disease, and everything that happens in terms of increase in disability without the appreciable relapse means that there is a progression that independent of relapses? I think the problem is slightly more complex, and the way I tend to look at these two composites is as orthogonal. We have the inflammation on the y-axis, we have the neuronal loss on the x-axis, and in the extremes you can see the relapse with full recovery or true worsening in the absence of any inflammation, whether that be clinical or radiological evidence or biological evidence. But we have a number of categories in between, and recently there is a new category emerging: the progression independent of relapse is active with some MRI activity. And what I'm asking here is part of the PIRA actually contributed to by this subliminal inflammation that we are not yet able to detect with clinical methods? And is some of the PIRA that we are seeing potentially a reversible worsening which corresponds to the subclinical inflammation? Of course, this is a classification problem, and would be an ideal, with the appropriate information, would be an ideal substrate for a machine learning to sink its teeth into, classify different ways of accruing disability according to the measurable patient characteristics. So to conclude, from the clinician's perspective, there is still an existing gap, a substantial gap, that prevents us from using AI and its outputs in clinical practice. And part of that is due to the lack of the translatable language, part of that due to the lack of some of the concepts that I mentioned. There are a number of areas that are really inviting for the use of this methodology in the future, such as individual prognostics, prediction of treatment response, identification of meaningful patterns, whether clinical, radiological, biological, and importantly also latent processes of which progression is a part.
And from technical perspective, I didn't want to list some methodologies here, but in my mind, what's more important is that to overcome the challenges, as Thomas mentioned, we need consistent communication between healthcare and AI. And not all of the roots of challenges are related to technical complexity. Lisbeth mentioned this morning that it starts with fair data, but that should not stop there. I think you already got this badge. We believe as a group, as the MS Data Alliance, that data saves lives, but we should support this statement by providing essential prerequisites for making this come true. And I think key is a consistent education. Thank you.
Thank you very much. Data saves lives, but it takes time. And unfortunately, due to time restraints, we don't have, there is another meeting afterwards, so we don't have time for questions. Thank you very much, all four speakers and for the audience. Thank you very much.